I may push back to chapter 2. Test date, I thought we were farther along in this than we are. Okay, so performing arithmetic operations. Well, we pretty much know how to do arithmetic, but there's a couple wrinkles we need to be aware of. You know, we know how to do addition, subtraction, multiplication, division. There's a couple more that we're going to keep track of. There's floor division. Not every language has it, but this one does, so we're going to count it. There's floor division, and then there's modulus, which means remainder. And I think I've mentioned that a little bit, but let's go ahead and talk about it. What's really important, besides knowing what the two new ones do, because we know what multiplication means, is the floor division and the modulus. So, you know, we know what 1 plus 2 is. 1 plus 3 is. Yeah, that's going to be 4. We know what 1 times 3 is. That's 3. We know what 1 divided by 3 is. Well, let's point out to a huge number of 3's in this language, more than in a lot of others. Let's find out exactly how many 0.3's it will display. So I'm not going to even write a program. I'm just going to type it into the shell. Yeah, that's quite a few. All right. Why am I saying that? Because a lot of languages will declare floats and ints as 8-bit values, and you'll get about 8 digits there. And we're seeing a lot more. We're seeing, you know, out to there, so it's probably a 16-bit value instead, which some languages call longs or doubles. A double being a double-wide float. And then we know what 1 minus 3 is, negative 2. How about 1 floor division 3? Floor division just means round down. So, what is 1 floor division 3? If you divide 1 by 3, you get that, but then you round down and you get, come on guys, what's 0.3 rounded down?
0.3. Or even just 0.
No, we're rounding it to an integer. Sorry about that. Round down to an int. So it's got to go to a whole number. I didn't say that. So it's going to go to 0, right? Yeah. Yeah. And then lastly, okay, so then floor divide by 3 is, or floor divide by 3 is what? It's 1, right. Everybody getting out? We're getting a lot of silence here. 4 divided by 3 is what? Why? Because it's not 2, right? It would have to be 6 divided by 3 to be 2. Everybody knows what round down means. Round down, go to the next whole number. So 4 divided by 3 is 1.333. If you round it down, it's 2. No, it's not.
Dude,
it's 1. Yeah, thanks. All right. So what about 4 modulus 3? Well, when we did 4 divided by 3 round down, we got 1. But what was left over, integer-wise? We had a remainder of what? So let's think about this. 3 modulus 3. Can I type? 3 modulus 3. Is there any left over? Well, when I do 3 floor 3, it just goes to 1. And 3 modulus 3, there's no remainder. It went in evenly. 4 modulus 3 rounds down to 1. 4 modulus 3, well, when we did that rounding, we had 1 left over. So we had a remainder of 1. 5 modulus 3, I keep saying that, 5 floor division 3 is what?
1.
Yeah, it's still 1. So 5 modulus 3, how many ints were left over? 2. Yeah, exactly. And then 6 modulus 3, not 1, it's 2. And what was left over?
0.
3, right. 0. I cannot talk today. My brain is fried. Okay, there we go. Haven't woken up from the weekend. There we go. So why would you care about modulus? Well, what if you had something like this? There are 16 ounces in a pound, if I'm correct. And the task was convert a number of ounces to a whole number of pounds and ounces. For example, if you have 20 ounces, that's 1 pound, but then how many ounces were left over? Yeah, 4 ounces left over. So 20 ounces is 1 pound, 4 ounces. And if you were going to go the other way, you know how to figure it out. 2 pounds, 2 ounces. I should just call it OZ, right? 2 pounds, 2 ounces. That's 2 times 16 plus 2 more. That'd be 34. So if we were going to do it the other way, 34 OZ is 2 pounds. And then how many is left over? Well, each pound is 16, so 2 pounds is 32, so there were 2 ounces left over. That leftover is key to thinking, oh, we could use modulus for this. And we're doing floor division for the pounds. So we could do something like this. Input the number of ounces. The whole number of pounds is equal to the ounces floor division, excuse me, yeah, floor division 16. And the number of leftovers is equal to modulus 16. Let's walk through this and make sure it works. We're going to do 17 ounces because we know that that's going to be 1 pound, 1 ounce in our head. So we input ounces. It's 17, and then the pounds is equal to 17 divide floor division 16. What's that? Kind of gave it away just a minute ago.
1.
Yeah, it's 1. Everybody clear on that? Floor division 16 rounds it down. So we're going to have 1 pound, and then 17 modulus 16. What was left over after we did that floor division?
A 1.
Yeah, so there we go. 17 ounces is equal to 1 pound, 1 ounce. How about cents? We're going to do cents. 100 cents in a dollar. So we input the number of cents, and then dollars is equal to cents floor division 100, and then the cents becomes a cents modulus 100. Let's work that through. Say that we have 233 pennies. We know what that's going to be, right? We know that that's $2 and how many cents? Let's check our equation to make sure it works. So dollars is equal to 233 floor division 100. So what's 233 floor divide 100? Yeah, but floor division means round down. Round down to the nearest whole int. I'm glad you're answering though, because I'm hearing a lot of silence. So 233 divided by 100 rounded down is all the way down to an int. Come on, guys, if you hand somebody 233 pennies, how many dollars are they going to give you?
2. 2.
Right. That's all it means. 233 floor division by 100 is 2. And yeah, in other terms, you could round down to 0.2, right, or point, you're right there, but you're not right as far as floor division is concerned. Floor division means to the whole, to the nearest whole number, to the nearest it. All right, and then we're going to finish it off. And so 233 modulus 100, after we did 233 floor divide 100, we got 2. How many cents were left over?
33.
33, right, okay. Cents, there we go. Might assign a program like that. Maybe tons to, pounds. How many pounds are there in a ton? I think it's 200, 2,000. Yeah, so we could do that. Homework idea. Tons converted to whole number No, pounds converted to whole numbers of tons and pounds. Okay, this is going to get a little bit weird, but we know that in our system, there's 25 cents in a quarter. There's 10 cents in a dime. There's 5 cents in a nickel. So if we wanted to convert cents to quarters, dimes, nickels, and dollars, not dollars. I guess we could have done dollars too, but we've already done that. 100 cents and a dollar. See, we're taking rolls of pennies to a bank and we're getting dollars, quarters, dimes, and nickels back. Hopefully they would have been whole numbers, right? But too bad. What if we tried to short them and we put 33 pennies in a roll? Okay, so dimes, nickels, and cents. That's what we want. So our equation is going to look something like this. Input, cents, and then we got to take care of the largest one first. So dollars is equal to cents, floor divided by dollars, round it down to the nearest dollar. Adjust our cents by that quantity. Cents is equal to cents modulus dollars, so that we get the leftover pennies. And then we keep going. Now we got to take care of quarters. Why don't we just write this one as a little bit of a program? Just typing in notes is boring. Alrighty, so file, new, file, save as. Don't save it in your Python directory. I say that every time. Okay. June 18. Your name, the date, finishing chapter 2, concepts. So if we'd done a pseudocode, it would look like what I was just starting to type, input. But we know that every time we do an input, we're going to print the prompt. How many cents to convert? We got to get our input and we got to convert it. So cents is equal to input, and now we got to convert it. Important thing to remember is you only do conversion if you're turning it into a number. If you ask somebody for their name, you don't call a conversion function. Now we've been using float, but I'm going to use, I'm going to convert it to a float, but I'm going to take it one more step. What if they typed in 12.0? I really want these to be ints. Floor division and stuff like that, I want these to be ints. It's possible that I could get away with using them for floats. You know what, let's see if floats work for modulus. That's my big concern. Can we do a floor like if we have 133.3 and we modulus it by, 10? It actually works, but we get some kind of weird rounding error. So I do want to round it to an int afterwards. I convert it to a float. Now I'm going to turn it into an int. You see, I did 2 steps. I asked them for a number. Well, 3 steps. I input it. I turned it into a float. I turned it into an int. I could have skipped, and these should be s's. I'm forgetting the s's on my variables. I could have skipped the float step entirely. But if you try to convert directly to an int, you get a little bit of a problem. Let me show you what I mean. X is equal to string 3.3, just like you'd get back from an input function. Now we want to turn it into an int so that we can do whole integer math on it. And it blows up. It says you can't do that. I don't know what a 0.3 is when I'm trying to change it into a whole number. So what we're doing is we're converting it to a float, and then we're rounding it down. We could have also just used a round function, I think. What is the round version of x? That might be more fun. No, there is no round function. My mistake. Now I want to take it to a float, and then I want to do a round of the x. Okay, so rather than, I could have done it this way. I could have also done this. I'm just going to add a comment here. This would have worked as well in this case. Now the round function is kind of cool because you can also round it to tenths, like you were doing, or hundredths, right? If you had 3.333 out to infinity and you wanted to round it to just 2 places, you could round it to 2 places with the round command, with the round function. I think you just do it with comma 2. Comma 2 would mean round it to 2 places. Want to round it to hundredths, that would be 3 places. But okay, I hope that's kind of clear. Why are we doing that? We got to convert string to a number. So we converted it to a float, but then we wanted to make sure, then we want to go to an int. We could have left it a float, but then we saw that rounding error. I'm going to demonstrate the rounding error one more time because that's actually a good one that I hadn't spotted before. If you do the integer version of 3.3, you're going to get 3. But if you do 3.3 modulus 1, you get something strange. I wanted modulus to give me a whole number. I'm spacing out. I don't remember my exact error. I'm going to skip that for now. Okay. So, if you're going to use modulus, it's kind of best for it to be an int if that's what you're hoping for. All right. Now we can start calculating the numbers of quarters. I still have these errors here. What's wrong with this statement? It would give me a syntax error, boom, right away. I have my cursor on it, so what have I done wrong?
Left off the S.
Yeah, I left off the S. If my variable name has an S here, I better do the exact same thing here. Better do the exact same thing there. Okay. I'm going to use QT as an abbreviation for quarter. Quarters is equal to cents floor division 100. No, 25. Apparently I skipped dollars. It's all right. And then cents is equal to cents modulus 25. That takes out all the quarters. Like if you have 99 pennies, 99 floor divided by 25 is going to be 3 quarters. Now let's keep on going with dimes. DM is equal to cents floor divide 10. And then we have to correct that for our new number of cents. Cents is equal to cents modulus 10. Now I'm going to do nickels. Nickels, I should have just typed out the whole word, is equal to cents modulus. Now how many cents are there in a nickel?
5.
5, so we're going to modulus, we're going to floor divide it by 5, and then we're going to remove those from our currency. So cents is equal to cents modulus 5, and then whatever we have left over is the number of pennies. Pennies is equal to cents. Whatever we have left over at that point. Why don't we just leave it cents? At this point, whatever is left in cents is our pennies. Okay, now we can print it out. I'm going to print out like 4 things in a row. So I'm just going to make kind of a little template for me to follow here. Then I'm going to copy and paste. Right? What do I mean by that? The first one is going to say quarters inside the quotes and QT outside the quotes, and then, 3 other things. Just saving a little bit of typing. You can type the whole thing in too. You don't have to do it that copy-paste way. Alrighty, so inside the quotes, I'm going to fill in quarters. And what is my variable name? It's QT. Inside the quotes, I'm going to put my English string, which is dimes. And then I'm going to fill in DM as my variable name for dimes, which I put up here. Then I'm gonna print out nickels. NICKELLES. And my abbreviation was NK. And then for the last pair of quotes, pennies, which was equal to our leftover cents. I hope I got that right. I'm going to run it and see. All right, how many cents to convert? 333. 13 quarters, 0 dimes, 1 nickel, 3 pennies. Yeah, that's probably right, but I'm going to pick one that I can add up in my head. 1 quarter plus 1 dime plus 1 nickel plus 1 penny. So that's 25 plus 10 is 35 plus 5 is 40 plus 1 penny is 41. So I'm going to run it again and give it 41 because I want to see 1 straight down. Okay, that looks good. And if I type in 0, hopefully it'll run zeros all the way down. All right? Okay, good. All righty. That's one example of using modulus. In my mind, that's the best example that I've come up with so far. So if we were going to add dollars to our calculation, it would need to go up at the top, right here. DL for dollars. Hate using lowercase l because it looks like 1. You could have used the whole word. I'm being lazy. I'm going to use the whole word. And then you're going to want to print it out down here. So what is the calculation for dollars?
The cents floor divided by 100.
Yep, cents floor divided by 100, and then our cents, leftover pennies, are going to be what?
Would be cents equal cents modulus.
Yep, modulus 100. Now I'm going to take my comment away. Please don't take my comment away. Okay. And then I'm going to add one more print statement for the number of dollars.
Got it.
Good deal. Good deal.
I kind of want to add $half in here now.
Yeah, why not? $half.
Alright.
Do you remember we had $2 bills?
Mm-hmm. Shoot, I have one in my pocket somewhere.
That's cool. Like an idiot, I spent the $2 bill I most recently got, and I was thinking, that was cool, I should have given it.
Right?
Yeah, that's looking pretty awesome. Sure, that's totally cool, and that's what you need. Let's run it. Unless there's a typo, that's perfect. Chico.
No, there's no mistake in there.
All right, do 333 just for fun. So that should be $3 and some stuff left over. Oh, see, DL is equal to cents. Just because each time we've done cents, so not dollars. Modulus 100, it's going to be cents. Modulus 100. One more line up. Go cursor, one more line up. Yep. Now compare that to this line. QT is equal to cents divided by 25. What are you going to make that to match it?
modulus in this sense. We don't have any dollars yet. So
Ah, gotcha.
Yep, you got it.
Gotcha.
Okay, cool. You're welcome.
Gotcha.
Alrighty. Now, one more thing to note. Now that we've, what's that term for that? We're not quite beating a dead horse, but we're getting there. How about order of precedence? Order of precedence is the order in which you do your math. And we already pretty much know this from earlier math classes, high school or junior high or whatever. What do I mean by that? If you do 2 times 3, 2 plus 3 times 4. If you type that into a calculator, 2 plus 3, and you hit enter, well, 2 plus 3 is 5, and then you do times 4, and you get 20. Well, that's not how we're going to do it. If you have one of those cool calculators that let you type in an entire expression, what's that going to be?
14.
Yeah, because 3 times 4 is 12. You got to do the multiplication first. So that gets calculated like this.
One question for us.
I missed a symbol. Back here I need to do one more symbol on my slides. This language, and not every language has one, exponent. What does that mean if you do 2 star 3? It means 2 times 2 times 2.
2 to the third power.
Yeah, 2 to the third power, exactly. Okay, so hopefully I don't have to talk about that too much, but I'm going to be talking about order of precedence, so we're going to mention that real soon. Okay, that's different than 2 times 3 plus 4. In that case, you do the multiplication first, but it's at the beginning, right? 2 times 3, that's 6, plus 4 is 10. Right. So, anybody ever learn a cute little phrase for remembering the order of precedence for math operators? PEMDAS.
Something like that.
Yeah. Please excuse my dear Aunt Sally. And I didn't make that up. Please excuse my dear Aunt Sally. Okay, what does that really mean? What does a P represent? Parentheses. How about E? That's going to be exponent.
Multiplication, division, addition, subtraction.
Yeah, and then M and D are multiply and divide. And by the way, floor division and modulus are also the same priority. And then that leaves AS for addition and subtraction. So we have 4 priorities of things. That's the first thing you do. That's the second thing you do, or the computer does. So that's the third thing we do. That's the fourth thing we do. Now, when you're talking about something on the same level, you just do them left to right. It's not like you do all the mults first and then all the divides. Or you don't look for all the additions and then all the subtractions. If you actually try that, you can get into errors. I don't remember an example of that right now, but I probably could come up with one. So just remember that you do all the parentheses first, everything inside parentheses. You do all the exponents, you do the multiplications and divides, and then you do the additions and subtractions. But if you have more than one thing on the same level, you just do them left to right. Alrighty. So what's the very first thing we do there? Now I didn't add any parentheses, so we can skip level 1. Then what? What's our level 2 category?
Exponent.
Exponents. Right. So we got to do our exponents. Do we have any exponents in our equation?
No.
And as a matter of fact, we do.
Oh, you?
So yeah, right there. Easy to miss. Okay, so 3 plus what is 4 to the power of 2? That's 4 times 4, which is 16. I'm kind of doing each step Would you really do this? No, when you just, kind of do it in your head or with pencil and paper, you wouldn't rewrite each step, but you get why I did that. Now what's the next thing we do? We don't have any more exponents.
We move on to step 3, which is multiply and or divide.
Right, so we got to take care of our 1 multiplication. So 3 plus 16 plus 10 plus 1. Now we're all in Cat 4. We're all in level 4, and that 3 plus whatever, that's 19, 20, 30. Hope that makes sense. And if I throw in parentheses in, that just groups it so that you have to do everything inside the parentheses first. So, for example, parentheses, come on, 1 plus 2 to the power of 2 in parentheses plus 3. A little bit different, but same idea. We're not going to tell ourselves to do the exponents first, even though that's kind of a natural thing. Instead, we're going to tell ourselves, first, do everything in the parentheses. That's a whole separate expression. Then once we're inside the parentheses, we can think, oh, we better do exponents first. And so in that case, you got 1 plus parentheses, 1 plus 4, and then outside the parentheses, plus 3. So inside the parentheses, you add 5 plus 3. So that's 8. And if I ask you to figure out an expression like that, don't type all the steps. If you feel like doing it on pencil and paper, great. If you feel like just doing it in your head, that's great. If you want to type out some intermediate step in order to help you, that's great. Whatever helps. You just don't have to take it to the degree that I did here. If I was going to redo this expression and I did want some help of typing it in, here's what I would do. I would have that expression, I would replace that with 16, I would replace that with 10, and then I'd be ready to go. Right. I wouldn't necessarily type all 4 lines. Okay, so that's PEMDAS, P-E-M-D-A-S. Just remember that not all languages support exponents, but they all support all the rest. Not all languages have a floor division, but they all have a modulus. Why don't I just copy and paste this into our notes? That's not our notes. That's our notes. Feel free not to type all that in. When I copy and paste, I know that it makes it hard, but it is in your notes. Okay. So the rules of precedence, we know those now. Integers are whole numbers. This is telling us some information that's not strictly true. It's strictly true for C and C++ and Java and stuff like that. So I am going to mention it, and then just tuck away in your brain that Python is its own little odd beast. So, I am going to put a comment here. In other languages, integer division is special. How? If you divide by an integer by an integer, it does floor division automatically. So in Python, 4 divided by 3 is equal to 1 point, up to a certain number of decimal points. In most other languages, since 4 and 3 are both integers, it does integer division, which rounds down. So in that case, for example, in Java or C++, 4 divided by 3 is just 1. And that can bite you in the butt when you're doing calculations. And what do I mean by that?
get the wrong answer.
Exactly. I'm trying to think of an equation that has like a half in it or something like that.
5 divided by like 2.5?
Yeah, let's pretend, and this isn't the real one. Let's pretend that the volume of a pyramid is 4/3 times the base times the height. You know what? It's probably something similar to that. Let's see. Let's go look it up. Volume of a pyramid. Yeah. See, it's yeah. So if we wrote it down, it'd be 1/3 times the height times one of those edges squared. And do you have to remember that equation? No. But the point that I'm trying to make is that if you did this, volume is equal to 1 divided by 3 times the height times the edge squared, which is a perfect representation of this equation. In one of those languages, this would what? What is 1 divided by 3 rounded down? It's 0.333, but if you round it down, it becomes 0. And so 0 times height times edge, it's going to say that your volume is 0 no matter what. So in those languages, what you do is you make one or both of those floats, and it works. So that's fine for Python. But in the other languages, it would be the same thing, just 1.0 divided by 3.0 times the rest of it. Hope that makes sense. Just tuck it away in your brain. Python works the way we would expect. If you were a programmer who had programmed in those other languages and then moved to Python first, then Python seems like the oddball. So all those other textbooks you'd buy will tell you, just like this one did, that an integer divided by an integer is an integer, that it rounds down. So just burn that away in case it asks it on your MindTap exam. Get the right answer there. And then I'm not going to ask that question on the exam. You know, I'm not going to say, how does it differ between one language and the other? If I was going to do that, I would use floor division. So this is just saying that if you have two integers in those languages, it automatically does floor division. And it's just a quirk of programming that things behave a little bit different in each language. It makes it fun. Alrighty, modules. Now we're getting to the good stuff. What are modules? Modules are functions. We've been using functions like int and float and print. All of those are functions. Now I'm going to use the term modules and functions interchangeably. The textbook uses modules all the way through. Other textbooks call them functions, or something even odder, methods, depending upon which language you're using. I could tack that on here, but what I really want you to remember is modules and functions. I will try to use modules most often, but when you leave this class, remember that functions are modules, and so if you're taking C programming and it tells you to write a function, it's just a module. And here we go. They're also called subroutines, they're called procedures, they're called functions, and they're called methods. Why do we have to have so many names for these things? I don't know. I guess that somebody in the 50s came up with one name, and then a person in the 60s thought it'd be clearer to call it something else. And in the 70s, they came up with another term, and in the 80s, they came up with methods. Okay, so to call a function, you get to use its name, and you put parentheses after it. So, a module is a named block, or named block of code. You invoke it, you call it, or your code does, you don't call it. Calls it by name, followed by parentheses. So if we wanted to, we could go back to our code and eyeball the functions real quickly. What's the very first function in our code? Usually a print statement, and then what's the one after that? Input, you know. So examples. Print, input, float, int. We've used all those. But we can write our own. What if we wanted a function called square so that we could do this? Here's what we want. X is equal to the square of 3. Now, sure enough, we could just type 3 times 3, or we could do 3 exponent 2. But let's just pretend. So here's how we would define a function. In pseudocode, we would do this, square x, and then inside it we would say set result equal to x times x, and then we would come back here and we would do return result. Now it's annoying that they give us that syntax for pseudocode. I may wind up changing our syntax a little bit because this is what it looks like in Python. And remember that they are two different things, and if I ask you to do pseudocode, I want you to do pseudocode. Even though it's simpler and looks more like programming for dummies. We gotta learn them both. Okay, here's how you do it in Python. Define square, and remember that every time you start indenting, in this language you have to have a colon on the line above it, and it has to be at the end of the line. And then you ignore the word set, result equals x times x, and then you do return result. Okay. So what are the differences? I don't like the way this tabs it, because the return statement is untabbed in good old pseudocode, and it's not in Python. And I would really like all of our module definitions to start with DEF, even if the book doesn't show it. So in all my examples, the pseudocode is going to have the module defined with the DEF keyword. Just to burn it in. You'll see a little bit different in the book. They won't use the DEF keyword. That's okay. Leave it out if you want. Put it in if you want. Got to put it in the Python. So I'm going to add a couple comments. This is the pseudocode version. And this is the Python version. So if you eyeball that, the only difference then becomes dropping the word set and indenting the word return. And if you gave me pseudocode and the word return wasn't indented because you wanted to make it look even more like Python, I wouldn't ding you for that. Okay, so I'm going to scroll this down a little bit. And here's what I'm going to do is write a function that asks the user for a value and then cubes it and prints the result. Same idea. So input value. I'm not sure what to call my variable name here. But this was supposed to be pseudocode, so I should have started it with the word start. I should have tabbed input value. And then I'm just going to call this C for cubed. Bad variable name. C is equal to the cube of the value, and then output C. That's our pseudocode for it. But it's not the whole story, because cube is not a built-in function. We're going to have to write that function ourselves. So I'm going to put that above the start statement. Do you have to define your modules above your code? Well, not in all languages, but in Python you do. So in my pseudocode, I'm going to do the same thing. Flowcharts are a different matter. I might not, put my modules first or in the leftmost column, because flowcharts can be in any order that you want. Okay, so here we go. Let's define our cube function. The book would leave the word DEF off. I'm not going to leave it off. So define cube x result is equal to x times x times x, or x to the power of 3. Since we're doing pseudocode, technically I should put the word set in front of it. That's another thing I wouldn't ding you for not doing. And then return the result. This is our Python example, pseudocode example. Please tell me I started the recorder again. Good, okay. Pseudocode showing a function. Showing the definition and usage of a function. When you access a function, there's two programmer terms for it. One is either invoke, and the other, simpler, call. I'm going to call that function. That seems great to me, but invoke, another term. Using a function, you could call it calling or invoking. Now, why do you do that? In this case, it's kind of moronic because it's just one calculation, right? But you could make a function that performs a long series of calculations. You know, if you're doing a physics problem or something like that, you may have a series of calculations rather than just one. Same thing for, you know, calculating compound interest calculated over a certain number of years based on, you know, an initial starting value and stuff like that. That's a fairly long, hairy equation that you wouldn't necessarily want to type in every single time. So you could put it in a function called interest or something like that, and then you can just access it. Another reason for putting things into modules is that if you have a mistake in it, you can just fix it in one place. Like, what if I forgot that the cube function meant x times x times x? What if I just thought it meant x times x? And then I use this, you know, 100 times in my code. I had that equation embedded in it, x times x or whatever. You know, and in other places I had it called c times c, and then in other places I had it called d times d, you know, whatever. If I put that calculation in one module and I figure out that's wrong, you know, where it said x, or cube x, cube c, cube d, cube value, whatever, I could just fix it in one place. So modularizing your code is the art of breaking your code up into chunks with names. And you do that to make your code more readable and more maintainable. If you have a 300-line program, but you can break it into 4 chunks, then your main code can just be calls to 4 modules. And then the rest of your code are those modules. And so then when you're looking at it, it's easy to follow the flow. It can be difficult to look at a program that's hundreds of lines long if it's just a straight block of code. Kind of like breaking a book into chapters, right? It's easier to understand if you break a book into chapters. It's easier to understand a program if you break it into modules. So, a module is a subunit of a programming problem. You want to use Professor Thompson's definition for it? It's a named block of code. Subunit, programming, named block of code, pretty much synonymous, really. Also called subroutines, procedures, etc. I'm going to use the term function interchangeably with modularization. I will call it modularization whenever I remember, since that's what the book calls it, but I may slip. To call a module is to use its name. Modularization, breaking down a large program into modules, which is called functional decomposition. Decomposing sounds like a bad thing. You know, the body was decomposing in the woods or something like that. But in programming terms, it's a good thing. You know, what is ultimately decomposition? If that body is, sorry for the grim example, if that body is decomposing, it's breaking into its component parts, right? It's being reduced to cells, you know, that aren't connected anymore. And modularization is the same thing. You're decomposing your program into individual chunks. And we're going to do a program that involves graphics as my example of modularization. So modularization provides abstraction. That's so that you can pay attention to the important properties while ignoring the non-essential details. For example, if we had to write all the code that did a print statement, that would be pretty nasty. If we had to write all the code that did an input, that would be pretty nasty. And it would probably differ based on which operating system you were running. It's nice to be able to ignore all that and just use a function name. That's called selective ignorance. I don't know how the input statement works, but I get to use it. I don't know how a print statement works, but I get to use it. I don't know what code behind that conversion from a string to a float is. Fortunately, I just get to use it. So high-level programming languages basically use an English-like vocabulary where one broad statement corresponds to dozens of machine instructions, and even better, or including with that, you can give a batch of instructions a name. And so modules provide another way to achieve abstraction. Also allows multiple programmers to work on a single problem. I could tell you to go write the database code. I could tell you to write the code that calculates the payroll, and then I could tell you to write the code that does the electronic transfer with the bank to do direct deposit. Right? You could have teams of people working on it, and you can be sure, like in any large program you see, any complex program you see, word processing program, a game or anything like that. Unless it's an indie game. Indie games are cool because they can still be written by one person, but they're not as large, right, as Call of Duty or whatever. So you can get multiple people working on the same one. Rarely does a single programmer write a commercial programmer. Usually you have teams. Usually you have teams of people working on it, and then you have another department called the testing department. And then you may have a third department that maintains the code, meaning that you've set your main programmers off to work on something else, but if any bugs are found, you have some people working on fixing the bugs or adding some new features to it. So you can assign each module to an individual programmer or to a team of people working on that. And if you have hundreds of people working on it, you'll have some people who are doing graphics, subroutines, and some people who are doing the communications with the primary server. You break it down. Break complex tasks down into individual subtasks, or else the program is just too large to write. Now, unfortunately, all of our programs are small enough. Well, fortunately for you, they're all small enough that one person can write them, but that doesn't show cooperating on them. And I should make it so, okay, you three guys write, these modules, you guys write these modules, and then, you stitch them together. But that gets really hard to manage, so I don't do that. Allows you to reuse work. Once you write a graphics module, you can just put that out there for other people to use. Like the people who developed Quake, and then they sold their graphics routines to other game developers to also write, first-person shooters. You can be sure that they wrote them as modules, and then they got, quite rich, licensing those modules to other people. Allows individual modules to be used in a variety of applications. These Windows programs that Microsoft gives us, they have a whole bunch of modules in common. Why? Because every program that they write needs to be able to handle a menu. Or if they have that taskbar up atop, that so-called ribbon up along the top, they have common code for that. And they have common code for handling what happens when you scroll. Or when you do file save, don't crash on me, then it pops up this dialog that's calling a common function, and it may be customized a little bit, but it's calling common modules in order to do that. That way, when somebody is writing a new program, when somebody at Microsoft is writing a new program, then they already have this body of code that the other programmers have written, and they can write a program much more quickly. They don't have to write their own file selection dialog and stuff like that. And then Microsoft publishes a lot of the code to do this kind of stuff because they want to encourage other people to program for Windows as well. So they bundle this stuff into libraries. A library is a collection of modules. We're going to use the Turtle library in order to draw pictures in just a second. Well, more in a second. While I'm here, I do need to save my notes. I would be sad if the computer crashed and we didn't have our notes. Where did I come up with June 31? That could not. Was it the 13th? I don't know. I probably uploaded some notes so they're completely wrong name. Okay. I don't see any Unicode. We'll roll with it. Okay. So library, although I don't think the book introduced the term yet, is a collection of modules. And reliability. You can test each module. You can sit down with another programmer, you can both look at the code, and in some programming shops they even pay to have two people sitting at the same monitor, the same computer, and you take turns typing. That would drive me up the wall. But they do that because you've seen it. When I'm up here, you can go, hey, you forgot the colon, or whatever. You know, you can catch my errors as I'm going along. Same idea of programmer teams. But similarly, you can have what's called code review, where you go and you look at the modules and you think it through. Yeah, that's going to work. Or you give your code to somebody else and they just write some test code, right? It's easy to test that cube function, right? You just call it and then you eyeball it, you know, and make sure it's the same, or you could automate that testing. So your main program is just the basic steps of the program. And then when you define a module, we use these three terms: the module header, the body, and the return statement. In our code, that's the header. In our code, that's the body. And in our code, that's the return statement. So, header, example, DEF cube. The body, result, or set result, either way, is equal to x times x times x. And did I have to call my input variable x? No, just remember that the variable names are important to us. The computer doesn't care whether we call it x or whether we call it, I married an axe murderer, whatever. It could be anything. And then you have a return statement. Python makes the return statements optional, but if you're returning a value, it's not optional. So I'm probably going to put return statements on all of my code, even though it takes up a whole extra line, that I have to scroll up and down when y'all are seeing it. So turn result. This is the module definition. Every module has a header, a body, and a return statement, either implied or actually typed into your code. What do I mean implied? In Python, if it's not actually returning a value, you could skip the return statement, and then the next unindented line of code is considered the end of the module. I'll give you an example of that. No, we won't. We'll do that when we get to the turtle code.
So if you don't indent the information in the body, it's not loaded.
Okay, please repeat. I'm sorry.
If you don't indent your information in the body,
You absolutely do. You have to indent. Yeah, let's put indentation rules. The header, okay, indentation rules for Python. The header begins with DEF and ends in a colon. In Python, every time you see a colon, you know that the next line is going to be indented. Every line in the body is indented, including the return statement. For pseudocode, it's the same, except you don't indent the return statement. I'm not going to count you off if you don't do that. Okay. In pseudocode, same rules, except you don't indent the return statement. All right, we've been here an hour. Why don't we take an 8-minute break? Please get back by 1:20. All right, guys, we're going to change lanes for a little bit. We're going to visit a site called How to Think Like a Computer Scientist. The whole name of it is How to Think Like a Computer Scientist Using Python 3.0. So, what it is it's a Python-specific site. So what I'm going to do is I'm going to go to Content, Online Reference, choose How to Think Like a Computer Scientist. And this is where you want to dig into to learn the Python language. Now, the textbook mentions Python, but it's not Python exclusive. This is customized, optimized just for Python. So, chapters 1, chapters 2, and chapters 4, we just hit the idea of modules and functions, but we have certainly covered the idea of 1 and 2. But just to show you how it explains things, we're going to go ahead and go into chapter 1. Oh, I used to have an extension that would boost the font size without boosting the scrolling. Alrighty. So the Python programming language, it's an example of one high-level language. There are other ones, C++, Java, etc. When you launch Python, once you launch Python or idle, it pops up the Python interpreter. The interpreter is the shell. That's where you can type in things like 2 + 2 and it immediately spits out 4. You can execute Python commands in there, but your program is when you string more than one Python command together into a so-called script. You can call it a program, you can call it a script. Each term could be used interchangeably in this language. When you go on to other languages like C++ or Java, you will not call them scripts, they're just programs. So scripts have the advantage. If you're just typing stuff into a shell, it's kind of a one-time use thing. But a script can be saved to a disk, it can be printed, it can be emailed to somebody, and so on. And we've been doing that. You've been saving your scripts and uploading them to me. So what is a program? A program typically does some variation of this stuff. Input. That's reading data from the keyboard or a file or some other device. Your joysticks, whatever. Output. That's displaying data on the screen. Output can also be saving your data to a file, or uploading it to the internet, saving it to a database, that kind of thing. Math. Performing math operations on it. That's what computers were originally written for, is to do math. People in the 40s would be astounded at what computers do today. And then conditional execution. Check to see certain conditions and execute the appropriate sequence of statements. You've run out of lives on your program, on your game, so the game ends and it goes into a waiting mode, waiting for you to press start again. You're writing an air conditioning program to automate your house. Once the temperature gets past a certain threshold, you turn on the AC. Once the temperature gets past another threshold, you turn it off. And then repetition. You perform some action repeatedly, usually with some variation. Not sure why they add that, but yeah, you're going to perform an action repeatedly. These are loops. These are if statements. For output, we've been using print. So what is debugging? Well, programming is a complex process. And because it is done by human beings, although people have tried to write programs that write other programs, which is a scary thought, Skynet or whatever, it often leads to errors. Programming errors are called bugs. Now there's, more than one kind. There are syntax errors. People don't call syntax errors bugs, typically. But once the program is actually starts running, and then it crashes in the middle or gives you the wrong answer or whatever, people call it a bug. And just for giggles, Grace Hopper first bug. So the first example of an actual bug being found, September 9, 1947. Now back in 47, computers were vacuum tubes and relays. And she found a moth that had been caught in the relays, causing the relay to not work. So she posted a page in her notes saying this is the first bug. Now, really, the term bug predates that. It was an electrical engineering term, but you know that was the first computer bug. Har har. Okay. Grace Hopper is an example of how the early programmers tended to be female PhD professors because the males have been drafted to perform different tasks, you know, the engineering, the electrical engineering and stuff like that, and there weren't very many female engineers, but there sure were a lot of female mathematicians. An interesting movie that I strongly encourage people to watch is called Hidden Figures. I'll reiterate that. Watch Hidden Figures. You can find it on Netflix or whatever, probably. There we go. So syntax errors. The program can only execute if it is syntactically correct. It follows the logic. You have typos in it, won't run. If you don't have a colon at the end of the if statement, it's not going to run. If you don't have the statements after the colon indented, it's not going to run. This is all the Python syntax, and other languages have different rules. But you always got to spell all your variables correctly. And by correctly, I mean if you define it with a capital letter, it better be used capital F all the way through. Or I left the S off the word since, so that didn't work. So for humans, syntax errors are not a significant problem. You could read poetry if there's no periods in it, like E.E. Cummings wrote, or you know, if there's misspellings in it, you know, the teacher can still read the assignment, you know, the paper you turn in, even, you know, if you don't capitalize things or put the correct syntax. But programs aren't the same way. They have to be precise. A runtime error is when the program crashes during running, or it's an error that does not appear until you actually run it. Meaning it starts running because there weren't any syntax errors, but then it crashes. An example of that is what I was showing you when it tries to convert. Now don't type this because I'm just going to delete it immediately. But what if I did this? X is equal to input. Now at this point, X is a string, and then I say print X plus 2. You can't add 2 to a string, so this is going to be an error. But it's not a syntax error. It starts running, but if I type in something, 5, it blows up. That's a runtime error. It occurred at runtime. Must be string, not int, because my input statement always returns a string, which is a series of characters within quotes. You can't do math on a series of characters. The computer has to have it boiled down to a number before it can start doing math, which is why we always do that x equals float x, or x equals int x. In order to convert it to a number we can actually do math on. So that's a runtime error. And then semantic errors, logic errors. The program doesn't crash. It doesn't so-called generate an exception, different kind of crash. It just doesn't do the right thing. You know, Pac-Man's running around on the screen and he dies for utterly no reason, even though there weren't any ghosts near him. That's a logic error. Or he passes right through ghosts without being killed. That's a logic error. You know, the player would like that, but the people who want to get, you know, extra quarters when your game ends aren't going to like it. So that's a logic error, a semantic error. So the problem is that the program you wrote is not what you wanted to write. You made the air conditioner turn on when it got too cold in the room, not too high. So the meaning of the program, its semantics, its logic is wrong. So experimental debugging. I can't figure out why my program doesn't work. It's not producing the right output. It's giving me the wrong calculation for the area, for the volume of the pyramid. You know, so you go, I cannot figure out why it's giving me 0 for the volume of the pyramid. Now what you do is there's a couple of ways you can approach it. Some languages, some development environments let you step through your code line by line, watching the variables change, and that's called interactive debugging. If you don't have interactive debugging, you can at least put print statements in it to see how far it goes. So for example, if I had a bug in my program here, I'm going to delete this stuff. But what if I had an error down, you know? I could put print since here just to see if my calculation got wrong. Now, like I said, don't add this. I'm going to delete these. And I might put a comment saying what this was. Step 1. Or just, you know, just a little debug. Debug 1. Like that. And then, you know, then I was still concerned about since at this point. And so that might be debug 2. And then I was concerned about the dimes and the cents at this point. You know. Okay, so then I run it. And how many cents to convert? Well, 333. And then I see my debug messages pop up. And then I go back and I compare to my code. Was cents really supposed to be equal to 33 at that point? Were the dimes actually supposed to be equal to 0 at that point? And so on. So you can add debug print statements to your program in order to figure out what is going wrong. And it's totally cool to be texting me, asking me, you know, taking pictures of your code and sending to me. But at a certain point, you're going to be getting the experience where you ought to be able to figure out some of these things. So generally what you do is you start with a small program and then you start adding to it. You can't write a 10,000 line program just from beginning to end like you were Stephen King mad writing it, you know, a novel. Yeah. What typically you do is you break it down, you start very small, and then you start adding things to it. Kind of like we've been doing in our class, right? We write a little bit of a program and then we add on to it and we add on to it, kind of snowballing it. For example, Linux is the operating system kernel. It contains millions of lines of code, but it started out as this really short program that Linus Torvalds used because he had an Intel 386 chip. He wanted to see how it works, so he wrote an itty-bitty little program that would just switch between displaying 4 A's and 4 B's. That's all it was at the beginning. But then he started writing it, you know, more and more and more code to control the 386 chip, and then eventually he wrote an operating system based around that. Some of the stuff I'm going to scroll past through, but I would recommend you read all of this stuff, just like you read the text. It's written in a very clear, easy to understand way. All right, end of chapter 1. Chapter 2, variables, expressions, and statements. A value is one of the fundamental things that a program manipulates. You add 2 plus 2, it calculates 4. That's a value. You're going to print out hello world, that's a string, that's a value. But values are subdivided into different data types. Integers, floats, strings. We're going to see another data type once we start using the turtles. If you're not sure what class a value falls into, Python can tell you. I could pop open idle, pop open the shell, and if I don't know what a whole number is, I could type, oh, what did they just tell me to type? Type, the word type. And the type of a whole number is an int. The type of a number with a decimal point is a float. The type of something surrounded by quotes is a string. And the computer treats those differently. Python does a good effort at mixing ints and floats so that they can be used interchangeably. But inside, they're stored in completely different binary formats. And so it's up to the language to do the conversions necessary. And like I said, Python goes to some way to avoid us having to think about that. So variables are things that can hold values. Named places in memories that can hold a value. Here's a variable named n that holds the value 17. It is an int because it's a whole number. This variable, pi, gets assigned that value, and it's a float. This variable has that name, it has that value, and the type of that one is string. Now tips. When reading or writing code, you should say to yourself, n is assigned 17, or n gets the value of 17. Don't say n equals 17. Well, I'm sorry. I'm going to say n equals 17. I know why they make that point, though. Because if you're writing an if statement, if n equals 17, you're still saying n equals 17, and it has a completely different meaning, right? You're comparing two values rather than setting a value. So Python has keywords. Keywords are built-in parts of the language. They define the language itself. Words like if, while, and there's a lot of other ones too. Return, def, else. Why don't I see else listed here? It's there.
It's underneath break.
Ah, okay. Yeah, right there. You might want to keep this list handy. If the interpreter complains about one of your variable names and you don't know why, it's probably because it's on this list. For example, if you're trying to calculate somebody's raise and you use that as a variable name. Now I have no idea what the raise, I do actually. But, so if in your code you were trying to calculate somebody's raise, so you started it right off the bat with raise 0, or raise equals 0, that's probably going to be a syntax error. And it says invalid syntax, and you go nuts going, there's absolutely nothing wrong. Well, notice that it's a different color. That's Python trying to give us a hint as to its purpose. No, not Python, idle. The idle editor colors things differently. For example, if statements, else statements, define statements, return statements. They're all orange. If these colors aren't clear to you, you can modify them. You can go to options, configure idle. You could say that highlighting, I want all of my built-in functions not to be purple, that I want them to be, bright green.
Now, does all compilers do that, or just this one does it?
If it's called an IDE, an integrated development environment, it probably has this. For example, Visual Studio, which you use for Microsoft programming, has it. If you use Eclipse, which is cross-platform for a lot of different development, it does it. NetBeans does it. Most programming editors do it because it gives you so much information about it. Okay, so now if I click my function calls are going to be bright green. Now that's pretty horrible. I don't actually want that, so I'm going to go and undo that change. But a subtle change to it might make those function calls pop out a little bit more. And not all languages color things the same way. Choosing red was arbitrary for this particular language. You could have made them green or blue or whatever. Whatever helps you read the code. I'm not going to change them though. So programmers generally use names for the variables that should be meaningful to the human readers of the program. So what is a statement? It's the instruction. We've only seen assignment statements so far. Well, that's not true. But x equals 3 is an instruction. Define cube. That's an instruction. Return is an instruction. Print is an instruction. It's a group of code, typically one line. One line of code per line. One instruction per line. Evaluating expressions. An expression, things like this. Hour times 60 plus minute. Minute divided by 60. That's an expression. A series of values separated by operators. And operands are the pieces of data that the operator works on. Exponent is an operator, so 5 and 2 are operands. Multiplication is an operator. I have to install that Zoom, sorry. Text Zoom Chrome extension. It says it's in there. Why don't I see it? Oh, he is. All right. Drag that over here. All right. Okay. So I can go back here and I can just zoom in the text. Yay. So, beginners sometimes confuse meaningful to human readers with meaningful to the computer. So they think that because they've called a variable average or pi, it will somehow magically calculate average or pi. No, you have to assign the value 3.14 to pi, and you have to calculate the average. So you'll find some instructors who deliberately don't choose meaningful names when they teach beginners. Not because it's not a good habit, but because we're trying to reinforce the message that you, the programmer, must write the program code to calculate the average. All right, I've done a little bit of that here. I called this variable value here, but when we passed it into the module, that's what's known as a parameter right there. It has a different name. I could have called it value here as well, as long as I changed all these x's to value as well. But I'm trying to break the concept apart of that being equal to that. The value that gets passed in is called an argument. The value that the module receives is called a parameter. And they are in fact two different things. If we did this, x equals 17 in there, and I'm going to delete that line. If we did this, it doesn't change the contents of that variable, right? It only changes the contents of x. Whatever we passed in, that's still the same. It's like we're taking a photocopy of the value variable and giving it to this function. He can do anything he wants to x. We still have our original. So I'm going to undo that line now. Okay. Am I missing my colon here? Go to your notes if you were typing it in. And this, no, there's not supposed to be a, never mind. This was pure pseudocode, so no colon there. But I don't care if you put a colon or not. Sorry though. Sorry for that mistaken digression. So we have type converter functions. We can convert an int to a string. Not that we've been doing that. We've been going from strings to int, but you can do that if you wanted to. I'm going to give an example of that. I'm going to go back into idle, go back into the shell. You know, I could do this. I'm just going to say A is equal to dollars, and I'm going to say B is equal to the string version of 10, and then I'm going to say C is equal to $sign plus A plus a space plus a B, and what do you know? Oh, why? Because I didn't put $sign in quotes. C is equal to quote $sign plus A plus a space plus a B, and then when I print out C, it's going to say $10. Now I actually should have put the $sign in front of the number, right? But anyways, you see that I actually had to convert this number to a string in order to be able to add all of these strings together to make a new string. Because you can't add numbers to strings in this language and have it magically work. Now, we could print doing this fashion, but fortunately the print function in Python just lets us separate everything by commas, and it doesn't matter whether it's a string or an int or whatever. It works okay. But you can convert things to a string with that str function, just like we can convert things to a whole number with int, or to fractional numbers, floating point numbers with the word float. Order operations, PIMDAS. Like I said, I'm scrolling through this stuff, but it's not a bad idea to read this. Input. Here's a now, if we were using something called PyScripter, apparently if you use the input function, it would actually pop up this cool dialog. That's kind of neat, but we don't have PyScripter. Feel like installing it? Feel free. We do have one called PyCharm. I'm not familiar with it, and I don't teach it because every installation of Python comes with idle, but you have to install PyCharm separately. If you feel like trying other Python development environments like PyScripter or PyCharm, they are more powerful than idle. You want to become a guru? Feel free to install PyCharm or PyScripter, and there are other ones as well. Composition. Composition is the art and practice of turning equations into expressions. For example, area is equal to pi r2. Can we type that into a program? Well, we don't even have a pi symbol, but you might be able to find it in Word and copy and paste or whatever. It has to be area equals pi, a variable name, not the symbol, times r. And we couldn't just do r2. We'd have to do r star star 2. Right? So area is equal to 3.14159 times r star star 2. So if we were going to do that volume of a pyramid, volume is equal to, I'm actually going to try to insert equations here. Where's the equation inserter? Well, if this is going to take too long, I'm not going to do it, but come on. It's on the ribbon. Select the Insert tab, find the Equation button on the far right. All right. Insert. Oh, right there. Okay. And I want, it gives me some built-in ones, but that's not really what I want. I want 4 or 3 over 4 and then I'm going to multiply this times height times width and then depth. Height, width, depth. Okay, so that's our equation. If we define these, you know, if we know what those mean. But that's not going to work. We couldn't type that into a computer and have it work. We'd have to turn it into expressions. So it would be volume is equal to height times width times depth divided by, or times 3 divided by 4. Like that. And you might want to, well, come on, Word, don't change things for me. You know, you might want to group things together in parentheses to make them even clearer. Right. But we could take that off. Anyway, that's composition. Composition is taking something like this and changing it into actual code, actual expressions. So the most important things to note about this are you can't just list things by each other and have them do multiplication. Works in math textbooks. It doesn't work in programming. So we just couldn't put HWD. We've got to put H times W times D. Let's give ourselves another one. I'm going to just make up totally a new equation. Alrighty. What's the composition for that one? I'm going to change this to X, Y here. Alrighty, so X is equal to, and what am I going to do next? How do I represent X and Y? They're by each other, which the textbook says multiply, but I can't multiply by just putting 2 letters by each other in a programming language.
X asterisk Y?
Yep. X asterisk Y, X star Y. All right, now I got to do this. Okay, what if this thing was so nice as to provide those? Whether it was or not, I couldn't just do that, right? I'm going to have to put another asterisk there. Even if this left them out, I'd have to put them there. I lost something in this. I lost my exponent. Oh well, no biggie. So what am I going to put inside the parentheses now?
X plus Y.
And
Would you be able to do another set of parentheses?
I'm going to have to do another set of parentheses. Exactly, because if I did this, what's wrong with that?
It would just do X plus Y divided by 4.
Right, it's going to be y divided by 4.
Yeah.
So instead, I'm going to do this. And once I did this, I could actually probably fix it just by doing that. That looks good to me. I think that's the same expression. You'll get.
It wouldn't be, right? Because no, it is.
It is. Now, what I had intended is for this to be an exponent, but I didn't make it an exponent. It would have been hard to read anyways. And in that case, it totally would not have worked this way. But it does work here. Okay, so that's composition. Composition is turning math formulas into computer expressions. The modulus operator. Okay, we're on to where this one. Hello, little turtles. We're going to write a little turtle program. What's a turtle? It draws stuff on the screen. The earliest turtles were actually little mechanical devices, kind of like Roombas. They had a pin on them, and they would draw on a big sheet of paper, and you would program it to go forward and then turn right and then draw another line. You know, it was a way to teach kids how to program. Because you could type in a program and then you'd have your turtle do it. Of course, nowadays we just do everything on screen. So let's give this a try. I think that we ought to start a new program though, because just tacking a turtle on to our code here would be kind of lame. So I'm going to do file, new file, and I'm going to create another one. June 18, turtle examples. I'm going to do file, save as, get it out of the Python directory, put it in my scripts directory, and I'm going to call it June 18 underscore turtle.py, just to distinguish it. Alrighty, now our turtle programs need to bring in the turtle library. Remember that I said a library is a collection of functions, a collection of modules. So we do import turtle. Now I want to create a turtle. Textbook calls it Alex. I feel like calling it Leo, like Leonardo, the Ninja Turtle. So Leo is equal to, and you have to capitalize this exactly, and you have to end it with parentheses. Turtle, all lowercase, dot, capital turtle, and then end it in parentheses. If you don't get that cap in there, it won't work. If you don't put the parentheses in there, it's not going to work. Now I'm going to make the turtle draw a circle. Leo.circle, and I'm going to type in parentheses 100. Then I'm going to make the turtle go forward 100 pixels and draw another circle, maybe even 200 pixels. You could type the whole word forward, or you could abbreviate it FD. I'm abbreviating it FD just because that's easier to type. Leo.fd, parentheses 200. And now draw one more circle of the same, of 100 width, radius. Leo.circle 100. Now let's run it. So drew my circle and went forward 200 pixels, it drew another circle. Now it went off the screen, but I could kind of stretch the window if I wanted to. Now the examples on the web page go into a little bit more detail. He creates a screen. If you can create the screen, you can also set the colors of the screen. At a certain point, he sets the color of the screen to, you know, light green. Let's go ahead and do that. We're going to add on something up right underneath the Leo command. We're going to create a screen, and we're going to set its background color, and we're going to give it a title. So I'm going to close that file. So okay, so under here, under creation of the turtle itself, I'm going to create the window. WN for window is equal to turtle dot, and again we have to capitalize the next letter after the dot. Screen, SCREEN, parentheses, in parentheses. Now we're going to change the color of the screen for whatever reason, and we're going to change the color or the title of the screen. So WN.BG color will change the color of the screen. WN.BG color, no caps this time, parentheses, quote, light green, no spaces. And I'll give you a web page that has a list of all the turtle colors. We're going to be going back to turtles just because they're a fun way to conceptualize modules. And let's give it a title. WN.title, T-I-T-L-E, parentheses, Leo the turtle. Now on my screen these numbers were too big, so I'm going to change 100 to 50 in each one of those cases, and I'm going to change that forward 200 to 100. Doesn't matter, these are just examples. And then lastly, we're going to tack on one more statement called main loop. I'm putting this at the very bottom. WN.main, M-A-I-N, loop, L-O-O-P. Nope, nothing, no periods after that. All right, WN.main loop, no spaces, parentheses, in parentheses. Notice that all these turtle commands are actually function calls. Every time you call a function, you have to use the parentheses. Sometimes you put things in between the parentheses. Those are called arguments, because otherwise how would it know what color or what title? Other times you don't. We had to put in arguments for drawing the circle, otherwise it wouldn't know how big of an argument of a circle or how far to go forward. But when creating the turtle, we didn't need to give it any arguments. When creating the screen, we didn't. When we call main loop, what main loop does is it just sits there and waits for the program to end. That's necessary in some environments. It didn't seem to be necessary in idle, but all right, there we go. It's waiting for us to end the program by clicking the X. All right, those circles aren't entertaining me too much. I'm going to do a walkabout and help y'all, but I want to type in one more thing first. I'm going to comment out those commands, and I'm going to change it a little bit. Leo.circle, I should have just copied and pasted. Circle 50, and then Leo.right, or RT would work. 90 degrees, right, at right angle. And then I'm going to copy and paste those statements 3 more times so that it draws 4 circles. And we can speed the turtle up if we want to with the .speed command. If you do Leo.speed parentheses 0, it makes it run as fast as possible. And as we write these programs and we get tired of waiting the turtle to draw complicated shapes, I'll be using the speed command. All right, let's pause. So we have our little command to draw our flower. What if I wanted to draw more than one flower? I wouldn't want to have to copy and paste these lines, 8 lines over and over and over. So I'm going to make this a module. How am I going to do that? Highlight all 8 of those lines. If you didn't put spaces in them, great. I'm going to remove the spaces. All right. Highlight those 8 lines and hit the tab key. Oh, and by the way, if you come up to Format, you'll see that there are 2 options, Indent, and then there are Dedent. Dedent is when you're tired of them being tabbed. You can dedent them. But I do want them tabbed. And now I want to define this as a function. DEF flower, DEF space flower, parentheses, end parentheses, colon. Now run your code and it's not going to work. Why? Because we've defined a function but we've never called it. So we're not going to see our flower. He just sits there. All right, you lazy turtle, you. Let's actually run now. Flower, parentheses, end parentheses. Now let's turn him to the left 45 degrees and draw another flower in the same space. So he's just going to turn a little bit. So after my call to flower, let me space this stuff up. After my call to flower, Leo.left 45, because I don't want to turn a whole 90 degrees. You'll kind of see why. And then draw another flower. I definitely need to add the dot speed command to give him a little bit of oomph. All right, there we go. So I have this flower module. I was able to invoke all 8 of these lines of code just with a single word by calling the flower function.
Okay.
Now we could spend some time improving the flower function by maybe allowing us to change the size of it, right? By specifying a different radius other than 50. We'd put a value inside, you know, the parentheses there, a variable inside the parentheses, and we'll do that later. Now let's do some code that will draw a square. Everybody got the double flower on your screen before I blaze on.
I don't have to think what that action.
Okay, so before I pause it, I'm going to go ahead and crank the speed of the turtle up, at least a little bit. So here, before I start drawing anything, Leo.speed, parentheses 0. 0 is the fastest, 1 is the slowest, and then larger than 1 gets faster and faster. Don't ask me why they made 0 even faster than 1, but 1 is the slowest, 0 is the fastest, and it drew it instantly. Okay, that's a little too fast. I'm going to change the speed to like 7, so I can at least see it draw. That's not fast enough. Change it to 9. Still not very satisfied with that. Oh well. How about 19? Does it go past 9? Okay, that's a little too fast. I'm being picky. 12. Leo.speed 12. That's still too fast. 10. Oh, come on. Isn't there a happy medium between too much coffee and still asleep? No, there's not. Forget it. I'm going to delete my speed command, but you can leave it on yours, your choice. Alrighty, how about drawing a square? How do you draw a square? You go forward and you turn either left or right, 90 degrees. And we do it for, 4 different ones, just like our circle up here. So DEF, and typically it's poor form to mix your functions in with your main code. And what do I mean by main code? Main code is all the untabbed stuff. So I might cut this stuff and put all the functions in one place. But just for ease of typing right now, today is our first day of functions, so, okay. So define square. And let's actually make this one take a variable for the size of the square. I could just call it x for short, Yeah, alrighty. So to draw a square, we got to go forward, and then we got to turn either right or left, whichever our preferences is. So Leo.fd parentheses x into parentheses. And we've turned right the other time, so I'm going to switch things up a bit and go Leo.left 90 degrees. And then I'm going to copy and paste those so that he draws 4 lines. But it's not going to work until I actually call it, the square function. Let's get him out of range of the other stuff, right? I mean, we've been drawing a whole bunch of stuff in the center of the page, so I'm going to send Leo.forward 100 pixels just to get him out of the way, and then I'm going to call the square function. And I want a itsy bitsy square, a square of size 10. But then I'm going to draw a square of size 20, and all I'm doing is cutting and pasting. A square of size 30, a square of size 40, and a square of size 50. I do need to crank his speed up. Oh well. Well, neat. I kind of forgot that I'd set the angle for him for 45 degrees. I was expecting him to go across. You can set the heading. And just like the compass directions, there's 360 degrees in it, so you can set it 0 or 90 or 180 or 270. But unlike the real world, Turtle considers north to be that way. So that's 0 degrees. And then up is 90. And then left is 180 and down is 270. But I'm not going to bother. I don't mind that, those squares being set off at a 45 degree angle. Now do you see what I mean? If we wanted to draw all those squares, we would have had to have repeats of these 8 lines of code. We drew 5 squares. 5 times 8 is 40. We would have had to have 40 lines of code in a row. Whereas instead we just defined one module and we called it 5 times. So this number down here, this 10, 20, 30, and 40, those are called arguments. These are arguments to the function. Arguments are the values you pass into the function when you're calling the function, when you're invoking the function. And then we have x up here. That's the variable that receives the argument. That's called a parameter. Now those terms kind of sound interchangeable, and you'll actually hear me mess them up. I'll say, okay, 10 is my parameter. No, 10 is the argument. X is the parameter.
For some reason, I can't get the squares to come up.
No problem.
It stops at the circles and nothing.
Same here. But I don't think it's circles now.
There should still be a wn.main loop, but it should be at the bottom of the code. Where'd he go? There he is. I kind of scrolled him off. I want you to do that. I'm going to put a little function definition here. Task. Write a triangle function that draws a triangle. Reminder, triangles, or a perfect triangle anyways, has, yeah, I see why you said 45, right? Because a perfect right angle would be, anyways, triangles has, or this triangle has 120 degree angles and 3 lines. And when I say right, do a DEF space triangle, and so on. And then make sure you call it as well. I'm going to stick these comments right above my main loop call, so that I can scroll the rest of this there like that. All right. So give that a try. Pause the recording if you're doing this at home. So something like that would be the first line of our module definition, and we called that the module header when we were looking at the textbook. Alrighty, so my triangle function is going to look a lot like the square function, except it's only going to draw 3 lines, and the angles are going to be 120. So leo.fd x leo.left 90, and I'm just going to copy and paste those so that we have 3 lines drawn. Like that. Now that wouldn't do anything because I never actually called the triangle function, so I'm going to put a call down here. Whoops. To actually call it triangle, and I want the first triangle to be sizable, so I'm going to make it 80. I want the next one to be smaller, 70. You don't have to use these same numbers. And then the third one to be a little smaller still. And I want to relocate him somewhere so he's not drawing in the same place as the boxes were. So above my triangle calls, you don't have to do this. I'm just going to do leo.forward. Just get somewhere else. 80 pixels away. Just so it's not drawing it on top of the squares. Now, what did I do wrong there?
You didn't change your 90.
I didn't change my 90s to 120s. Okay. Alrighty. Now, I want to make this code look a little bit better. And what do I mean by that? Really, the functions ought to all be in the same place. You shouldn't mix your functions in with your main code, the main code being the unindented stuff. What I'm going to do is I have this flower function up here. I'm going to copy and cut and paste my entire square function. And I just remembered that I said that I was going to put return statements at the end of my functions, and I haven't been. It does an implicit return when it hits the first unindented line. But I'm going to go ahead and tack on a return statement on my flower function. But then I'm going to cut the square code and paste it right underneath the flower function. And I'm going to tack on a return there, just to be book perfect. And then finally, I'm going to go and get my triangle function. Cut that. And paste it and add a return statement. And I really have this stuff indented too far, not that that's a problem, but I'm going to highlight all that stuff and choose format dedent just to get it right. Okay, now it didn't matter if you did that, but that's way more correct to define your functions like that. It could be that I could stick all this stuff even up at the top of the code at the very top, but I don't think that's true. I'm going to give that an experiment. Don't necessarily follow this until you see that it worked for me. I should put it underneath my comments though. Alrighty. How are you gonna work? Well, what do you know it did? Alright.
It worked exactly the same.
So, yes, and that's how it should be. It should work exactly the same. So I've defined all my functions above my main code. And my main code is the stuff that would have been the start and the stop, right, if I was doing pseudocode. Start up there at the top and then stop it down at the very bottom. Alright, we're going to do a homework assignment based on this, because homework is awesome. Let's Alright guys, there's going to be 2 sections to our homework. One is that since we talked about the equation for the volume of a pyramid, write a program that will ask the user for the edge, the bottom width, for the width of a pyramid, and calculate the volume and display the volume. We can go to our other code in the notes and steal that. Well, I guess since I'm in the equation editor, I've got to use the little thing that goes to the x. Alrighty. Alright. So if W equals width, volume is equal to 3/4 times width cubed. That's the formula. That's part 1. Part 2. Octagon and hexagon. And I bet some of y'all have already tried this. Modify the turtle code from in class to add an octagon module function and hexagon. I don't know why I'm capitalizing octagon. Have your program call those modules to prove that they work. And just for simplicity's sake, I'll copy and paste the code, into the assignment itself, so that you copy and paste into your program code. You don't have to put all this in one source, right? The pyramid isn't really related to the octagon and the hexagon, but if you want to put it all in one, that's fine. It's just, I find mixing turtle programs and regular programs a real pain. So I would turn these in. I would turn in problem 1 and 2 as separate programs. Alright guys, let's make a Dropbox for this and we will be done.
You want us to submit our notes for the day as well?
So Dropbox E, just refresh your Dropbox, you'll see E. Put in the programs that you wrote today. You don't have to upload any notes unless you just feel like it. And of course there'll be one for the homework pretty soon. Alright, I'll see y'all Wednesday. And adding one more comment to the video. My homework assignment had a glitch. I forgot that you have to also ask for the height as well as the width. So from our notes, I've modified how you calculate the volume of a pyramid. 3 divided by 4 times width cubed times height. And so that should be the expression that does it. Alrighty, until next time.